So last time I started describing various applications of Grover's algorithm. Applications in the sense that the problem is something different, but Grover's algorithm is used as part of the solution process. So, for example, I described the amplitude amplification in a generic scenario. I discussed what is the spatial search problem, and I will give some more applications of that side. It's a wide subject, and people have proved all kind of connections. I'm not going to go through the whole list, but give you some ideas about whatever the span of this particular algorithm, and what is important is a widespread nature. So let me see applications. So one of the extension which I described towards the end of last lecture was spatial search, where the database was distributed and we are trying to find out where the object is. And I gave the general strategy which involves spreading of the signal with a wave nature and then detecting with a particular oracle which is very specific or localized to the object you are looking for. It's more like a particle aspect. And the combination of the two gives you the best algorithms. There are two lower bounds, and for a lattice in a d dimension, I wrote down those two lower bounds. I can write it in a different notation. So the query's scale as the larger of these two numbers. This omega is another notation which is used to describe a lower bound. And one can understand in different contexts how this mixing of these two features arises. One way is to look at the dynamics of a non-relativistic evolution. So there is what you call a random walk, that is the classical process of diffusion, and it has a well-known solution which follows the dispersion relation, where omega representing the energy is proportional to k square, which represents the momentum. So this is just writing the position space equation and converting it into a momentum space. You look at Schrodinger equation as a d by dt on one side, which gives omega, and a Laplacian on the other side, which gives k square. So this is a non-relativistic. On the other hand, if you have a wave propagation, as you may have seen in many applications, the frequency is proportional to the wave number. It spreads linearly in time. And the difference between these two is essentially a square root speed up. This spreads much faster than this situation. You can just count it as a what you call simple dimensional analysis. K has a dimension of 1 over length, omega has a dimension of 1 over time, and so the time depends on the length in a particular manner. Here there will be a square root, a slower process compared to what happens over here. So this is essentially relativistic. And what happens in all these spatial search algorithms is a mixture of these two in a clever manner, which gives a square root speed up in the algorithm. You can even ask for all kind of peculiarities by changing the value of the dimension. And in particular, these two are dictated by different physical principles, and there is a well-known feature in study of what is called the critical phenomena in condensed matter physics, that when there is a mixture of two different kind of dynamical bounds, when they coincide, there are logarithmic corrections. They are coming from, in some sense, modes of the system which are gapless, basically zero energy modes. But in this particular case, that situation occurs at d equal to 2, and then the queries behave like square root of n log n. And this is the best known result. It is a correction on top of the Grover's algorithm, which only gives square root of n. But this arises essentially what are called massless or zero modes. And this result was derived by Tulsi several years here when he was a student in IISc, and it has stood test of time. Nobody has improved it after that. Actually, Tulsi improved all the existing algorithm up to that particular stage and found a better result. So this is one feature which is buried inside here. You can also look at situations where this database is just some set of points. Not necessarily you can describe it as a regular lattice of certain dimension. It can be just a graph. And then you can ask a question based on what will happen to the process depending on the connectivity of the graph. Generic results are not so easy to describe for arbitrary graphs, but there is one particular case which can be handled more accurately, and that is where the database distribution is a fractal. So a fractal is a different set of arrangement of points in a space. The regular lattice is based on generators which are translation. You have a point, you go a certain distance, another point, another translation, etc., with a uniform pattern in whatever dimensions you want. Fractal is generated by a step which is a recursion, not translation. Okay, so what is the difference between recursion and translation? The recursion have many scales, and you take a pattern and repeat that pattern at multiple scales. In another set of words, it is sometimes also referred to as a self-similar structure. And there are many examples of such fractals, both in nature as well as in physical models. So, they are self-similar structures with recursion as the generating step. For example, you can take a line and say that I'm going to delete certain segment of that line. Then you go to the next step, whatever remains, you rescale the size of the segment and again delete it and keep on deleting on and on. That will generate a fractal. If you have not seen a description of fractal, you go and look it up. It's not too complicated. But the peculiarity of fractals is that it has two different dimensional description. One is a position space and another is a momentum space. In standard lattices, the two descriptions are exactly corrected by say a Fourier transform or any such construction, and they have the same dimension. From a crystal lattice, you can go to the Brillouin zone, and from the Brillouin zone, you can come back to crystal lattice, no problem. They both have the same dimension. In case of fractals, that is not true. That the position space will have one dimension, and the momentum space, which is also referred to as a spectral structure, can have a different dimension. It is unusual, but you can actually demonstrate it. So there is a so-called Hausdorff dimension, which describes the density of points in space. And yeah, you have to say what will be the definition of dimension. The definition is just described by you take a certain region and you keep on changing the size or the radius of that particular region and ask yourself, how does the number of points within that region grow with the radius? Okay. In regular lattice, that is the standard dimension, that the number of points will go as radius to the power d. But in fractals, that d can be non-integer. And that is this something called a Hausdorff dimension. Hausdorff is the name of a mathematician. And the other one is a spectral dimension. And as the word spectral refers, this is defined in the momentum space. Same way you find out various eigenstates of momentum and ask, how do the number of states with a momentum below a certain value grow as you increase the bound of the momentum? And that number is a spectral dimension, and the momentum is defined via the usual operator in all these process is, this is the Laplacian operator which tells you what is the momentum definition, etc. And that this can be different in case of fractals. And then you can ask, does this kind of logic work? And the answer is yes. It can be shown explicitly by numerical simulations. And what turns out to be that it is a spectral dimension which describes the density of states that is important, and not the Hausdorff dimension which describes the density of points. Because actually what you are dealing with are the evolution of various states in that particular structure. So the whole thing is correct. So this sometimes, let me call it dH, and this one is ds, and this dH is not the correct one, it is ds relevant. For the spatial search problem. So these are some extra tidbits about spatial search. Many things have been worked out, and I'm just giving you a kind of summary. Let me now define a new problem which has the name collision problem, and the corresponding solution which comes from Grover's algorithm. So what is a collision problem? It again refers to a whole set of items in the database, and the job is to find out if two items have the same property or not, anywhere. And when they have the same property, that is called a collision. So one can make up many different scenarios. One of the easiest things to understand is you have a group of people, like in this class. Do they have the same birthday, any pair? How do you find it? So, well, that sounds kind of somewhat artificial. Okay, what will you use it for? But actually it is a very practical problem in analysis of traffic. For example, in internet, there may be multiple signals are flying around. Two of them want to use the same channel. Okay, that is a collision. What do you have to do? You have to find a solution. So you decide that, okay, one of them is going to wait, the other goes first, there is a queue, and the second one goes after. And this has to be done dynamically all the time. In the internet, things are flying around, and you have to always keep on figuring out how to make the queue and arrange various signals which are waiting in some particular sense. So that is a more practical version of this particular problem. So what is the classical solution? You can't afford to check for every pair. It takes too long. Because if you have n objects, pairs are n times n minus 1 by 2. The order n square, which can become very large. So the practical solution which actually is used is you take these n items and sort them in some labels. Sorting requires some effort, but as I have told you before, there are quick algorithms like heap search and quick search and various names like that, which scales like n log n instead of the pair checking, which will take n square. So it is better. So what is done is you have a list, you sort it, and then look at neighbors, which will go down the list from one end to another, checking for all the neighbors. If two neighbors have the same value, it's a collision. Okay. So that is the solution used in, say, internet traffic. That is a best thing which can be done classically. So now we have to ask, can I do anything better by these are quantum tricks? And I will describe a solution which uses Grover's algorithm. Okay. So let me write down the definition is two items have same property and find that pair. And the examples which I kind of gave were the same birthday or the same channel for internet traffic. It can be any kind of traffic, doesn't matter. And so on and so forth. So what the best use of Grover's algorithm in this particular case is, it uses a combination of the classical strategy and this quadratic speedup in the search. Quadratic speedup cannot identify a pair. It will find one item. And so you have to use some combination. But so best classical solution is sorting, which is so what will you do? How will you generate a pair that you will take a subset of the database as one object and the rest of it as another object. You have to create a pair in some sense. So choose, this is a quantum version. N to the power n third items and check for these collisions classically, this which is through sorting. So it will require effort which is n raised to 1/3 times log n raised to 1/3, which is, well, 1/3 times log n, so that doesn't matter too much. And if it finds an answer, well, just go ahead with it. But it can be that when you checked over here, you don't find any collisions. But then there are other items which are n minus this particular n raised to 1/3, okay, which are there, the remaining items of the database. So if that works, which is the solution is found, and you go to the next step. If it doesn't work, then search the whole database with these n raised to 1/3 items as targets. You already picked them, so you know exactly what they are, and you can treat them as the target oracle. That I can flip the sign of them if I want to use the Grover's algorithm. And then what is the complexity of this particular thing? So it needs effort, which is order the whole database divided by the number of targets, square root. That is the scaling of Grover's algorithm, which I described in the last lecture, and that is also order n to the power 1/3. Actually, the power 1/3 was chosen so that both these options have the same scaling. That gives the best solution. Otherwise, one of them will take more time, and you will have a situation like this, which will say that sometimes there will be more effort, sometimes there will be less effort, and that is not what you want. So that is the solution, so best solution, and it is significantly better than the one with through the sorting.
Like, if you have taken n to the power 1/3 items that we don't find, but like our other part of n minus the part, there will be a collision inside that which is not corresponding to this cell.
No, it will tell you whether there is any object inside here which matches with the target.
That is not exactly a collision.
Target will be treated as a superposition of this n raised to 1/3.
Yes, but like if like our other subset contains like two items with label AA, and our n by 3 does not have any label A,
Yeah.
and all other items are just randomly.
Yeah, so there can be failures, okay, in the sense that there is no overlap between this and this, there is no mapping, that probability is small. Okay, it's that kind of probabilistic structure will survive. You have assumed here that yes, there is some collision somewhere. Okay, so it's still probabilistic. With small So this is the argument for designing a solution to the collision problem in the quantum case. There is yet another version, looks similar, but they all matter in terms of mathematical construction. Which is something labeled as element distinctness problem, where the job is to check whether all the elements in the database are distinct or not. It's not the same as here, whether they are trying to ask whether there is a coincidence or not. This is just a different phrasing, turns a problem around, but the answer for this is very different than the collision problem. So for this element distinctness problem, again you can find an algorithm which combines Grover search with this quantum walk. In a clever manner. You have to explore the whole space, but then you are also looking for whether something coincides or doesn't coincide.
If we, after the collision problem solving, if we do not get any collisions
Yeah.
after the algorithm, that means all the elements in that space are distinct.
Yeah.
Then, can't we use the same collision algorithm to the
Probability is rather small. Probability is very small.
and to accommodate for that, we are giving you algorithm for implementation.
Yeah. So one is asking that some common properties there, find that pair. Okay, here it is a converse statement that check whether all items are distinct. These are means what I had described in some sense in a complexity language as complementary problems. That you are asking kind of inverse statements. One of the other example of this type is whether the number is prime or whether it can be factored. When it is factored, your job is to find the factors, which is little more than that. Here it is finding that pair, but there can be a situation where there are no other factors and you decide whether a number is prime or not. So it is in the same kind of logical structure that these problems are framed, and it combines all these things, and this problem was solved by Ambainis, name of a scientist, and he not only found us algorithm, he showed that it is the best algorithm. And the power here is different. It turns out to be n to the power 2/3. Okay. Grover's algorithm had square root of n, this is n raised to 1/3, this is n raised to 2/3. They're all power laws, but they depend on the context which you are trying to solve the specific problem. So these are means some variations, but I'm just describing as them as illustrations, and well, they all have this idea of Grover's algorithm buried inside it. There is, well, these things keep on going, all kind of variation. And I'm going with the answer, I'm not going to give the proof, but the purpose of is to not to give all the mathematics, but to give an idea about in what manner the same algorithm can be used in very different contexts. So one more problem is called quantum counting. What does it reply? That in the usual setting of Grover's algorithm, there is a database and you know the number of target states which you are looking for. But suppose that number of target states is not known. And the job is to find the number of target states. What will you do? So the Grover's algorithm generates rotation in the two-dimensional space at some uniform rate. That rate of rotation actually depends on the number of targets, kind of thing which I wrote down over here. And what we need to do is stop that rotation at the correct stage where you have gone close to the target states. If you don't do that, you are just going to go round and round in circles. So you need a criterion for where to stop to use Grover's algorithm, and that is not known if the number of targets are not known or known. Okay. So and then the algorithm just doesn't work in a straightforward manner because you don't know when to stop. And if you don't stop at the right point, you will go into some other state and you have no idea whether the answer is right or wrong. So you have to combine some other strategy with this uniform rotation, and that strategy is generally labeled as sampling. That you will try out stopping at various stages and then sample among those possibilities to find out whether any of those answers satisfy the criterion that you want. So sampling needed after some So you try one rotation, then try another one, then try another one, all of them with different angle. You'll get some answers. Then you check among those particular answers to find a good rate of success. And the algorithm then has a scaling which is different, and it can be parameterized in terms of the uncertainty or a bound in terms of how many targets are there. So I will write down again the answer. It's an interesting exercise in sampling if you really want to work through it. So for k items, k targets with you want to find this number k, and it will give you a probabilistic result, some error, which is some delta k. So you can say that I want to make delta k equal to 1, so that will give some particular value. Actually, this has some units, so it's better to normalize it. K is some number. What is the fractional error? Minimum thing you can get is a k known to plus or minus 1 or something like that, a discrete situation, and then the answer is correction to Grover's algorithm, which is the square root of n by k is just the scaling of Grover's algorithm. Total size of the database is n, k is the number of targets, but then you want to figure out what exactly the value of k is, and the penalty is this factor of 1 over epsilon in front. The more accurate you want, you have to require more number of queries or iterations. So this is yet another application, or you're just modifying the statement of Grover's algorithm in some different ways, what is known, what is unknown, and rearranging various things.
Do we want to count the number of targets?
Yeah.
So if you don't know the number of targets and the targets also, how will the algorithm know when to stop? And
No, you know the, what you call the oracle.
the algorithm is the database.
Yeah, so oracle defines what the target is. You just don't know how many of such targets are there in the database.
So the target values are known.
Target
The
value,
number of targets is unknown.
number of targets is unknown.
So the rotations make those like states to fall in the targets and counts each target.
Yeah.
And then maybe the number is given.
Yeah, so you have to determine the number. If you just say that I applied the algorithm and I found one target, doesn't tell you whether there are others around or not. So you have to work a little harder. That is why this sampling is needed. You try multiple choices and find the fraction in some sense of targets. Of course, you want to increase the accuracy. You have to give some parameter. What is that number? You have determined what accuracy, and there is a penalty.
And higher the accuracy means the sampling is much more precise.
Yeah.
Again, the accuracy.
So this is the uncertainty in the number of targets which you have calculated, delta k. K is the actual number of targets, and you want a more precise number, delta k becomes small.
And time also increases.
Time increases. Okay. So yet another version which goes under the name of fixed point search. What is the goal here? That if you just use Grover's algorithm, you are going to have this rotation at uniform rate. But can you stop the algorithm by some instruction inside the algorithm itself so that once it reaches the right place, it will not move ahead? Okay, you want to stop that rotation automatically. Here, everything depends on knowing the numbers of the items in the database and the items of targets, whatever it is. If you know the number, you know when to stop, but you don't know in certain cases, still you want the algorithm to stop. And that is called as a fixed point search, that yes, it will go from the initial unbiased state towards the target, but once it has reached the target, it will stop. Now, by the arguments which I have given, the Grover's algorithm is the best solution to reach the target quickly. And if you want to do that, then somehow you have to arrange the rate of rotation that it is large in the initial step, but once you get closer and closer to the target, the rotation rate becomes smaller. And that means the algorithm slows down. It is not optimal in the sense, and it will take more steps when you are closer to the target. So algorithm slows down when closer to the target. And the fixed point means that if you are right at the target, it doesn't move at all. Okay, that is a definition of fixed point in various kind of dynamics. You go, and once you are at the desired place, no further evolution. It's like an equilibrium. Yeah.
So this sounds something similar like the basic Grover's algorithm to find the target state in a database.
Yeah.
So what is the difference between the first, the normal search for target and this fixed point?
Yeah.
Both sounds.
They are similar, but the rate of rotation is now dynamic. Okay, here the rate of the rotation was uniform. Here you are going to adjust it so that you get closer to it. The algorithm basically slows down, and once you go to the target, the rate will go to 0, and of course the complexity depends on the rate. So if you are using a slower rate, of course it's going to take more steps. Okay. So it is not optimal. The question is, can you design something? It's a variation because this job cannot be achieved by iterative procedure. Because if you have a iterative procedure, it will say that what you did in the first iteration is the same as what you will do in the second iteration. But what will be in the third iteration is again the same. And then unitary evolution will just give you a rotation. That means all the rotational steps are going to be the same, and you will end up with this particular situation, which is what Grover's algorithm is. So you have to give up this iterative procedure and define a new kind of procedure. And Grover himself found a procedure to do this, and that is a a new kind of arrangement which is called a recursion. This recursion is the same adjective which I used in describing these fractals. So it means you will have multiple stages in the algorithm and you will do the same steps but at different levels. And this was again, the result was constructed by Grover himself. And there is a hierarchy of skills. And which goes as the operator at some nth level is, let me define it in a consistent notation. B as, okay. So initially you have some operator given, and this is the same kind of sequence of various factors which was used in the amplitude amplification process. So there is some initial operator which is given, which has a small success rate. So I will have to specify this object. What is the initial success rate? It is small. So I will label is as a 1 minus epsilon for the success rate. And then the next label, which is going to look like this by this rule. That by this iteration, which is a recursive scheme, if I am given V, I will be able to construct a new operator which looks like this. And then what is the success probability of that? And this relates these two success rate. One of them is 1 minus epsilon. The other one is 1 minus epsilon cube. And the point is that you start with some epsilon, which is always going to be between 0 and 1, because these are all probabilities. After one such iteration, the correction to 1 will become epsilon cube, which is much smaller than whatever epsilon is. And if you reach a stage where epsilon is 0, the algorithm stops. But there are caveats which one should remember. The first thing is this is the recursive construction. So given the operator at n minus 1, you know how to construct an operator at nth level. And if you write the corresponding sequence, you will see that it doesn't repeat. It will not generate an iterative sequence of what this V, RS, RTS, it never will repeat. It is some order, but it's a mixture of V, V dagger, RS, etc. in different combination. And that is how it is different than Grover's algorithm. That it's a recursive, but it doesn't repeat. And so the unitary rotation, whatever it is able to converge and stop. The other thing is, what are these operators? They are not the same as what I had written down earlier, but these are defined now by a specific combination. The P is still the projection operator, which is an outer product of, in this particular case, S with itself. But in case of Grover's algorithm, this value of alpha was equal to pi. So when you exponentiate it, you will just get identity minus 2 times the projection operator PS. Now, you can expand this thing out as well. And the series basically is very easy to construct because this projection operator have nice property that square of itself is the same as the original operator. So you can immediately expand this in a power series, and all the infinite series just collapses because PS square is equal to PS. And the result is the coefficient of 1 is nothing but the identity, but the coefficient of PS is the whole exponential minus the 1 which you subtracted out. All the higher order term in the exponential expansion just become PS. And the Grover's algorithm uses alpha equal to pi. So this is identity minus 2 times the projection operator. So this is here what Grover himself found is this identity holds when alpha has a specific value equal to pi by 3. So the vertical construction of this operator can be done by the same logic circuit which was used for Grover's algorithm. It is just combination of identity and a projection operator. Nothing complicated, but now we are going to use a different value of the angle. And that gives this dramatically different consequence that at every iteration, the error will become cube of itself. So if here there was error was 1 part in 10, one of these levels, error will suddenly become 1 part in 1,000. So it converges geometric progression very fast. The only point is the initial value of epsilons will be sufficiently small. If it is epsilon is equal to 0.99, then the cube will move, but it will not move very much. So it works well. When that means the initial success rate has to be sufficiently away from 0. In the Grover's case, the initial success rate for an unbiased database was just 1 over n. And if n is large, that number was quite close to 0. That will not give you a good fixed point algorithm because it will converge very slowly. And you can actually put a general value of n where epsilon is equal to 1 over n. So you lose all the advantages of the quantum dynamics if epsilon is the starting value you take as 1 over n. So as I said earlier, this algorithm is nowhere near optimal in comparison with Grover's algorithm, where there was square root of n. If you plug this thing in, the algorithm will turn order n. So you're not going to get any speed up. So it's extra requirement that epsilon has to be a finite number, not something as small as this. Then you can do a lot better. So how does this identity prove? It's a very simple exercise. By just plugging in the various numbers, I can illustrate it in some particular sequence. So let me try to just give a few lines of the derivation, not filling up everything, but some part in the middle. So I will write down this whole expression. So T, there is V, but now I'm going to plug in all these values in there. So it's identity plus e raised to I pi by 3 minus 1 times S, then there is a V dagger, then another factor, but now it is T. Then another factor, and then that. So I have to evaluate this whole combination, which is sitting inside here. How do I calculate it? Well, just expand it out, nothing clever which can be arranged. So there are, basically there are 2 terms over here and another 2 terms over here. So when you expand it out, there will be 4 terms. What are those 4 terms? So it turns out that this T times V times S remains a common factor. The first term is the identity from both of them. So it will be V dagger, V dagger, and V will cancel. And then all you have is a T, V, and S, which is what I have put outside as a factor. So that is 1. The next term is something which will involve one factor of this e raised to I pi by 3, either from this or from that. There are 2 such terms. And what will it involve? That it will have T, V, and S, which I have put outside. And then the other factor will have identity. So V dagger and V will just cancel out. And you will not have anything more left, because S times S is equal to 1. So this actually contributes 2 times e raised to I pi by 3 minus 1, once when you include this term, and the other time when you include the other term. And the third term is when you have the factor appearing twice, and then it will be TVS here. There will be S V dagger T, and then again TVS together with it. So it will be e raised to I pi by 3 minus 1, and this whole thing will appear 3 times, but one of them has this conjugated expression, so it can be written as TVS whole thing square. And that essentially is the calculation. You can write it in different ways. If you want, you can explicitly evaluate this complex number. E raised to I pi by 3 gives you a complex unit vector at angle pi by 3, and that has a real part which is half, imaginary part which is root 3 by 2i. You add up all those things, and the real part kind of cancels out. But it's a simple algebra which you have to do. What now you can calculate is this object T, V, RS, alpha, RS of pi by 3, V dagger, RT of pi by 3 times V times S. What we wanted was a success probability, which is the absolute value square, and then that means you have to take the absolute value square of all those things, and you have all the ingredients. This will get absolute value square, which is specified as 1 minus epsilon, and this stuff is also 1 minus epsilon, which is sitting over there. The rest of these are some complex coefficients. Just have to evaluate it. So it will give 1 minus epsilon times the whatever the whole thing square is, root 3i plus e raised to I pi by 3 minus 1. There's a square here. Okay. This factor came twice, and 1 minus epsilon which is this object, square it, do this whole simplification, and you will find that it is equal to 1 minus epsilon cube. This is 1 minus epsilon, and what this will become is 1 plus epsilon square, and these are the 2 factors which make up 1 minus epsilon. So that is essentially the derivation of this fixed point search algorithm, and it is useful provided you have a bounded away from zero success probability to begin with. It will converge well in those particular case, and you can probably design some applications in those kind of scenarios. So these are some examples of all kind of things which have been explored in different modifications of Grover's algorithm. What if this assumption is changed little bit? What if this assumption is changed little bit? How the strategy can be redesigned, and this set of whatever applications illustrates that. Okay. And it, for the same reason, has been incorporated in many different proofs as some version of subroutine for solving many kind of problems. So yeah, that's as much as I would like to say about it. And if you have any questions, just go ahead and ask. Because
we are using the initial V0 at minus Rs into RT.
there is no minus Rs. It is that was there in the Grover's algorithm. Here there is no minus.
So V is a unitary operator.
V is a unitary operator.
It's just that we are recursing it.
Hmm?
It's just that we are recursing it.
Yeah. So all these things, whatever they are still unitary operators. Rs, Rt, whatever exponential of various things. V dagger is unitary because V is unitary. So this whole product of unitary operators, everything is in the unitary evolution. But the operators at different levels are not the same. That is what is construction of a recursion. The first level, it is just V. Second level, it is this. Then the third level, you will take this whole combination and put it inside V and see what the whole expression looks like.
And small n is the number of iterations. So small n, number of iterations.
No, small n is a level. The n is a recursion level. So if I use a first recursion level, epsilon will become epsilon cube. If I used the second time, the epsilon cube will become epsilon to the 9. Whatever it is, cube of that. If I use one more level, then epsilon to the 9, sorry, not 9. Yeah, 3 times epsilon cube is equal to 9. Then it will be epsilon 9 to the cube itself. Next level become epsilon to the 27. So that is the way it will progress in terms of the recursion level and how the error will scale. Initial V is provided, that is the search oracle, whatever it is. But you want to evolve in a different manner.
That was Rs into RT initially.
No, this is on the framework of defining the initial state, as in the case was the amplitude amplification algorithm. It can be any routine. Okay, so in the amplitude amplification algorithm, I had written the operator as U. Okay, so it was some operator which could be more complicated algorithm. Only thing its success probability was small. And now I wanted to construct a new algorithm which success probability is large. So there it was done in a certain manner. This recursive version does the same job, but this combination is different, and it is able to increase the success probability and also converge to the final state where the success probability goes to 1. And it will stop. In the other cases, you will have to still know when to stop.
Success probability increases at the cost of.
Initial success probability is just this.
In the next recursion,
Yeah.
success probability increases at
Yeah.
the cost of increased number of gates.
Increase number of operations. So first level or the 0th, here I have written 0th, you use this operator only once. Next level, you will have to use it 3 times. V dagger and V. Still next level, you will use it 9 times. Okay, because each of this V will get replaced by this whole combination. So this power increases, but the number of applications of how many V's are there also goes.
But the number of operations goes faster. Means there are additionally R raised to power alpha, R to power alpha.
Yeah, so this, it's kind of trivial to say, if I have nth level recursion, this is going up in factors of 3, this exponent is also going up in factors of 3. So we'll say that one more level, I will have 27 times V used, but the error will have epsilon raised to 27, things like that. Yeah, so the Grover's algorithm had a very specific scenario where this initial state was just written as the Hadamard operator of acting on 0. Okay, so this V was actually h raised to n acting on 0. Here it could be some arbitrary thing, you are not specifying what it can be.
How do you explain the algorithm slowing down when you are getting to the?
Because the number of applications, no, here you say I am at nth level, number of times V is used is 3 to the power n. And the error, whatever it is, this number will become 3 to the n. So you have to count now how many iterations I have used and what will become the error. And it ends up basically growing as order n, number of counting of how many applications of V are needed to get error up to some particular accuracy.
But that is only when the epsilon is chosen as 1 by n.
In general, doesn't matter. But starting with the initial state where the epsilon is kind of bounded, algorithm will be fast. If it is not bounded, 1 over n is 1 Pascal scale, but it can be some other number close to 0. Even in that case, the scaling will be order n. Okay. So the next topic which I am going to discuss is Shor's algorithm for factorization of numbers. But before I go into the quantum part of it, there is a lot of classical stuff buried inside it, which is basically the subject of number theory. You have to define what is a prime number, what is a factor, what are the ways of looking for factors, etc., etc. Because you not only need to contrast the classical versus the quantum one, but actually you need to use a lot of classical properties to get to the quantum algorithm, because quantum algorithm is only some small part of the whole construction by Shor. Okay. So that I will just give a definition of what is factorization. So there are integers which integer, I'll have to give some value, so let me call it n. So it means you can write it as a product of two other numbers where these factors cannot be 1 or n itself. Those are always there, so you have to rule them out. And that can be tackled, and the way to tackle these things is, once you have put in those 1 and n, is to use what is called a modulo n arithmetic. The whole set of integer which is infinite can be cut down to this smaller set, and the notation for this modular set is z subscript n. So it goes from 0 to n minus 1, and then n is equal to again 0, again another n minus 1, etc., etc. And these numbers can be defined within that particular set, because whatever p and q are there, they are in between this 1 and n. So the first thing is to define the problem in this finite set. We are not going to deal with all the infinite set of integers. So what do we do classically? And well, what we did in kind of primary school is, given a number, you have to find a factor, then you check it one by one by all the factors that you know. 1 is ruled out, so you start. Is 2 a factor? That is actually quite easy to check, because you only have to look at the last digit, nothing more than that. Then you say that 2 is not a factor, then 3 is a factor. You go one after the other, all the prime numbers that you know. Is there a 5 factor, etc.? And how far you have to go? Well, you can go up to square root of n. Because if there is a factor, one of them will be smaller than square root of n. So you scan the whole thing one by one, and that is what we were taught in primary school. And that has a name goes after a Greek mathematician, and let me get the spelling of the name right. I think it is Eratosthenes. Okay. And it is called a sieve because when you check whether 2 is a factor or not, you remove all the even numbers from the set. Then when you check for 3, from whatever remains, you remove all the multiples of 3. So it is a successive narrowing down of the option, and that is why it is called a C. You just remove all the ones which doesn't have the right property, and it's check all factors, prime factors, not all. You have to know what the prime numbers are. And up to square root of n. And it takes a large enough time if n is large, because it's only some square root kind of thing which you get, nothing more than that. Of course, this is old Greek algorithm. People have discovered improved versions of this sieving kind of procedure, and that has a particular name, and it is called number field sieve, and that is the best classical algorithm known. So and it has a scaling, which is what I want to write down. It is not square root, it is a little bit different. There is a improvement. So there is a log n in the exponent, but it comes with another power of 1/3. If the 1/3 was not there, then exponential of log will just make it n. And the algorithm is linear in the size of the number, which is exponential in the size of the digits. But because there is a 1/3 power of here, it does a better job. There is no other simplification of writing this down. This is what it is. But certainly it is not polynomial either. It is not a polynomial of this log n. It's an exponential of some power. And this is the best known algorithm to factor these numbers that we know. That is what is used in our classical computers for all kind of cryptographic analysis. And what can be said is that this is a problem in class which is NP in terms of complexity, because this is not polynomial, but it is not as difficult as NP complete problem. NP complete problems are those where if you solve one, you solve everything. It's not in that category, but it is sufficiently complicated. So what do we do to convert this structure in a quantum language is not use this method at all. It uses an alternative definition. So So another strategy is actually worse than this. So you take an algorithm which is not the best classical algorithm. Classical it is worse, but the quantum version becomes better. And this is the kind of thing which you have to play with in many scenarios where you want to convert the classical strategy to the quantum one. Maybe the best classical strategy is not the one to study. Something which is worse in the classical case but has some nice structure inside it, that will give a better quantum answer. So all those things depend on the structure of what is useful in conversion to a quantum language, and many times these answers are different because the quantum logic is essentially different. And what is this strategy is convert this problem into what is known as a period finding problem, and I will just give the definition for that. That to define a function f(x) is equal to a to the power x, where x is a variable, a is fixed, and all the calculation is done modulo n, which is inside this particular field. And why this is periodic? Because with increasing x, modular n operation is there. So sooner or later, a raised to x will repeat. Okay, it can be the worst situation you can imagine is it will generate all the numbers from 0 to n minus 1, but then it has to repeat. There is no choice. This is a property of what can be called a cyclic group, which I had mentioned way earlier in the course, that if you take a power of a group element, it will, some stage, it will repeat. And when it repeats, a raised to r is equal to 1. The initial value for x equal to 0 is 1. And when it comes back to itself, some value a raised to r is equal to 1, and r is called the period. And now there comes the quantum trick, that what you have constructed is a periodic function. You can use Fourier transform to find the period, and the number theory will then tell you that if you know the period, you know the factors. So all those things have to be put together, which will follow in the subsequent lectures. So I will continue from this, that yes, you have defined a periodic function. First job is to understand how it will help you to find the factors. Because the quantum part is straightforward. I know a periodic function, I can do all kind of tricks with it using Fourier transforms.